Okay, this is section 8.4. We're going to be talking about how we can use sequences and figure out what the sequence is just based off a table or a graph. So as a warm-up, we're going to write down the nth term formula for an arithmetic sequence and a geometric sequence. So hopefully we've got these memorized at this point. So we're going to write a sub n equals d times n, so the common difference times the index, the number of the term we're on, plus a naught, plus that initial term, the 0th term if you want to call it that. And then for geometric, it goes like this. The nth term is going to be that initial term, and then we take the ratio and we raise it to the n. And hopefully we're pretty good at figuring this out by now. But again, just to point out, most of the time we're going to be using these nth term formulas. They're really nice. You can plug in any number that you want. If you want the 59th term, you plug in a 59. If you want the 4,000th term, you're going to plug in a 4,000. But there are some other names for it. So besides nth term formula, some people call them general formulas and other people call them explicit. So they're not talking about something completely different. They're just talking about a different name for the same thing. So we're pretty familiar with arithmetic and geometric sequences by now, but we ought to be able to recognize them regardless of the setting. So we've seen lists of numbers and things like that. We've also had problems that have said, okay, D equals this or R equals that. And from that, we've been able to figure out, hey, this is either arithmetic or geometric. And what we're going to do today is we're going to look at the same type of thing, but in a different setting. Now we're going to be looking at some tables and we're going to be looking at some graphs, but we're going to be picking out the same type of stuff, same type of information. So here's what we want to do. It says, describe the operation used to go from one term to the next term in the sequence. Find the next missing term in the table. Tell whether the sequence is arithmetic, geometric, or neither. And then write a general rule for the sequence. So again, general, we're just talking nth term. If you want to call it explicit, that would be totally okay. Now, before we get started, just a quick reminder. Unless we're told otherwise, the index when we're talking about sequences is going to start with a 1. So we're going to put a 1 right here. But when we're writing down these general formulas in both of these cases, we needed to have that initial term, that a naught. So when we're looking at a table or a graph, what we're going to look at is we're going to key off this one right here. We're going to key off the one where x is equal to 0. So as we go through and look at this formula or this pattern right here, this is kind of just like a counter. This is like the index. So if we were talking about this in terms of a regular sequence, this is the first term, this is the second term, this is the third term, and so forth. So this would be 8, 11, and so on. This would be the 0th term. So this is just a counter, and the sequence is actually where the y's are. So we're going to do 2, 5, 8, 11, and so forth. So to find the next term, what we're going to do is you can kind of just tell from that pattern, we're going to add 3. Well, if we add 3, my gosh, then the next obvious thing is, well, if we're adding the same thing every time, then we know that that's going to be geometric. It says, what's the next term in the table? Well, the next term in the table, if we added 3, would be 14. So we're going to put a 14 right here. And then we want to figure out the general formula. What is the general rule that would say what this is? Well, it's going to be like this. It's going to say, well, the nth one is going to be the common difference times n plus a naught. And the cool part about this is all we need to do is find a naught, and we're all set to go. Well, there it is right there. It's the 5. You can see it sitting right there. So what we're going to do is we're going to write down a sub n is equal to, we already said that the common difference was 3, so we're going to do 3 times n, and then we're going to put a plus 5, and that's it. There's our formula. Now, what would be cool is if we could say, hey, you know what, does this actually work? Well, what if I plug in a 3? What if I wanted to find the third one? Well, the third one would be 3 times 3, because we're plugging in a 3 in both places for the index, and then we're adding 5. Well, that would be 9 plus 5, and 9 plus 5 there's that 14 that we said it would be. And the other cool thing is we could actually replace this question mark at the end, and we could say, you know what? If this is an n, then the way you find the term that it corresponds to is going to be 3n plus 5. And then we're all set to go. So it's almost easier when we've got a table like this. So now we're going to take a look at the next one. Let's take a look at the pattern here. So we've got a half, then 1, then 2, then 4, and then the next one is missing. So let's think about this for just a second. So we've got a half, a 1, a 2. Well, you'll notice the difference between the two of these is a half. The difference between the next two is 1, and the difference between the next two is 2. So there's no way that this is arithmetic. This has got to be geometric. And what we're doing here is we are timesing by 2, or I'm going to write multiply by 2. So I'll just write mult by, whoops, make that look right, mult by 2, okay? All right, so what is the next term in this sequence? Well, we're just going to multiply by 2, so this next one would be 8. So if we multiply 2, we'd have an 8 right here. If we're multiplying by the same number every single time, that's going to be geometric. And now we need a general rule, and that general rule is going to look like this. It's going to be a naught, whatever the ratio is, raised to the n. So in this case, we need to know what's the 0th term. Well, in this case, it's going to be a 1, because that corresponds right there. That's the 0th term. So we're going to put a 1 right here. Common ratio is 2, and we raise that to the n. I am going to clean this up just a little bit. We're just going to write this down as 2 to the n. Circle that, and we're all set to go. Now, the key to doing this is making sure that we key off the right one. So we want that 0th term. That's going to be the one that corresponds to an x equals 0. So it's going to look like this. If you want to find a naught, you find the term on the table, or the ordered pair on the table that starts with a 0 for x, and then whatever y is, that's going to be a naught. Okay, so let's come down here and let's take a look at example number 3 and see if we can tell what's going on here. So this sequence is different, and let's see if we can spot a pattern here. So again, these are just the counters on the x. We're going to take a look at the y's over here. So 0, 1, 4, 9, 16. Let's see. So there's a difference of 1 and a difference of 3. So there's no way that it can be arithmetic. And let's see. You can't really multiply 0 by anything to turn it into a 1. So that's strange. And here you'd have to multiply by 4. We're definitely not multiplying by 4 again, because that wouldn't make a 9. So this one is different. So let's see if we can maybe think our way through and find some sort of pattern. This is 0, and then this one's 0. This is 1, and this is 1. This is 2. It'd be nice if that was a 2, because that's a really simple formula, but now it's 4. This is 3, and this is 9. And this is 4, and this is 16. Well, if I had to guess, you'll notice that every single one of these, and we learned these last year, these are all perfect squares. So if I were to just square this 5, I'd end up with a 25. So to find the next term, you square, we'll say it this way, we square the index. Square the index. Okay, so the next term in the table is 25, and this is not arithmetic or geometric, this is neither. And then a general rule for this would be this. Well, if you're just going to square the index, you take the index and you square it. So this would just be n squared. So just kind of an illustration that although we study arithmetic and geometric a whole bunch, those are not the only type of sequences. This is a nice clean pattern. It looks pretty easy, but it's not arithmetic or geometric. Okay, let's take a look at the back side here, and you'll notice that here we've got graphs. So it says starting with the points on the graph, it isn't any different than dealing with a table. It just looks different. In fact, if you think about it, it might be actually easier to identify which type of sequence it is. It says what's the common difference or ratio between consecutive points, and also what shape is it. So here's what we're going to look at. This one right here is the point 1, -1. This is the point 2, 1. This is the point 3, 3. This is the point 4, 5, and so forth. If I were to go backwards, this is going to be the point 0, -3, and this would be -1, -5. So I've kind of made my own table here. Now, the important thing is we're trying to figure this out is we've got to go in this direction. So notice that we've got a -1, then we've got a 0, then we've got a 1, then we've got a 2, and so forth. So the indices, the indexes, the counters are going this way. So we're going to go up this list. So this is going to be -5, -3, -1, 1, 3, 5. So you'll notice that the numbers are getting bigger as we go along, and you can tell that they're getting bigger by 2 every single time. So the difference on this one is 2. This is going to be arithmetic. And the nth term formula, remember, we're going to write down a sub n. It's going to be the difference times n, and then we need to add a naught. Well, a naught is really easy to find here because it's just the one with the 0 for the x. So it's going to be this one right here. So this is going to be plus a -3, so I'm just going to make that a -3. So there's our nth term formula. And then the other thing we want to notice is, well, yeah, this is arithmetic, but take a look at this. If we were to draw a line right here, that's a nice linear graph. So it's an arithmetic sequence, but if we graph it on a coordinate axis, we end up with a linear graph. So let's see if we can figure out what's going on this one. I'm going to do the same type of thing here. I'm going to write down the index, which is going to be the x-coordinate, and I'm going to write down the y-coordinate, which would be the term for the sequence. So this is going to be 2, 12. This is going to be 1, 6. This one's going to be 0, 3, it looks like. And this one's going to be -1, well, if you had to guess, I'd probably say that's about 1.5, about 1.5, okay? So, is this arithmetic, geometric, or neither? Well, it's definitely not arithmetic because you'll notice here we went up just 3 points and here we went up 6. So it can't be arithmetic. Let's see if it's geometric. If it's geometric, we're multiplying by the same thing every time. So to get from 3 to 6, I'd multiply by 2. To get from 6 to 12, I'd multiply by 2. And you could also do that little trick where you take a term and you divide it by the one before it. So if I do 12 divided by 6, I get 2. 6 divided by 3, I get 2. So this means the common ratio on this one is 2. So this has got to be geometric. And then the nth term formula, you'll remember, we just do the ratio, which is 2, raise it to the n, and then I just need to know what the 0th term is, which on a graph or a table is a piece of cake to find because it's just that one right there. So we're going to put a 3 right in front here. So it's geometric, there's the formula, and what shape is this? Well, if we were to connect these, we'd get a shape that looks something like this. Now you might wonder about what happens over here. Maybe it continues going down, below the x-axis or something. But remember, this is going to get halved every single time, so it's going to continue being positive, so it is exponential. So here's the bottom line with this side. So an arithmetic sequence is like a linear function for only discrete values. So it's not everything in between. It's not the entire graph. It's just distinct parts in between. So it only works for x equals 1 and 2 and 3 and so forth. And a geometric sequence is like an exponential graph. So we'll write exponential. And again, it only works for those particular points where they're integer values. So 1 and 2 and 3 and so forth. Okay? So we can, come back here, I'll zoom in on this just a little bit. We can interpret a naught to represent the y-intercept. And remember, a naught is sometimes referred to as the initial value, or the value when n is equal to 0. And once we have that, it's really easy to look at why our formulas turned out the way they did. So remember, with arithmetic, it was d times n plus a naught. So this is going to be the common difference. Common difference right here. So if you know the common difference, you just put that in front of the index. And then this is going to be the y-intercept, which we're going to call a naught. And then for geometric, we put the y-intercept right in front here, and then this is the common ratio. Okay, that's what we multiply by to get from one to the next. Okay. Hopefully that kind of gives you a good overview of what we've been talking about with arithmetic and geometric, and that there is this kind of graphic interpretation using a table or using a graph. And hopefully you're in good shape. So good luck on the assignment.